under here so I could be sure that it stayed at 1.79 degrees, and the loads that got up there, it still had a factor of safety of 1.5, but it was just right there at the bare minimum that's required by the FAA. And then I got to thinking, well, that's not how they fly it. You know, they fly it with the supported here, and that's it. So I took that block out of there and discovered that it was getting about top to Dwight and having to send out an actual spindle, and it's losing about a degree out of 1.9 degrees, which made it come out much better, much better. Here's that's a little point that this unit pivots about, and oh yeah, that's good. Oh, okay, not this one. You got that other one that's, yeah. Okay, this baby right here measures strain very accurately. This is just a flat piece of stainless steel sheet. It's about 30 thousandths thick. It's got a sharp lip right there, and so that, and a sharp lip that points the other direction on the other end. Picture this clamped down to the blade. It's got a C-clamp on top of it. So this end stays with the blade. This end is on the surface of the blade, and as the blade stretches, this end doesn't move. It stays where this end is clamped. Okay, you with me so far? This end's clamped. This end has the blade will stretch underneath it and move out. This end right here hits that little part of the little lever arm right there, and it makes this right on. And so it accentuates the travel at the dial. If you get 1/1000th of motion here, which is right here.
Disconnected.
Somebody's Bluetoothing into the.
Really?
I don't know.
Somebody.
We just realized that was Bluetooth to my phone.
Ah!
Bluetoothing in.
Okay, but anyway, 1/1000th of stretch on the blade would reach 7/1000ths of dial motion, so you could get you're reading something that the blade don't stretch much. And the way I calibrated that, you know, when you calibrate something, you want to, oh, Lord have mercy. You want to compare it to something that's known, and therefore that's what calibration is. So I've got this this hydraulic load making thing, and a load cell to relieve pounds. So I put a known poundage on this blade, and I know the blade is 1.27 square inches of aluminum, and so you know what the stress is with a good load, you know, 10,000 pounds and 1.27, it's going to run about 8,000 psi, something like that. And so I just adjusted what I would call this mechanical disadvantage to match that, and I'd get them to read identical. So I think that turned out pretty accurate. It did measure the average strain over about a 6-inch length. And so there's really parts in that strain that are probably stresses that are higher than the average value and stresses that are lower than the average value. But I moved it from this area right here. I'd go out to here, do a measurement, and then go back to here and do a measurement. And they were all pretty much the same, so even though it's an average value, there's not too big of a deviation from that average value. Huh? Bolts? Okay, like, you're losing it? Okay. Yeah, one of the main things I wanted to do was load the attachment area to failure, and it boils down to a function of what do you want to call a failure. At what point has it failed? Now you got two bolts on the root of the blade, Okay, I'm assuming everybody wants to hear about bolts. Okay, I got this part memorized. There's two kinds of bolted joints. There's a slip critical joint and then there's a bearing joint. The slip critical bolted joint relies on clamping force. You know, you crank a bolt down and it clamps on the two surfaces, and the coefficient of static friction between those two surfaces is what presents shear or resistance. So as the clamping pressure goes up, the retention strength of the bolt goes up. A bearing bolted joint is one that it could be a pin. It could be, it's all shear. It relies on shear force to keep the two surfaces together. As it turns out, this at 40 foot-pounds can be considered a slip critical joint, and this at 10 foot-pounds can be considered a bearing joint. This one here, and it gets even more complicated. I guess what I'm doing is I'm telling you all the reasons why doing the calculations to determine the effective resistance that bolts present is really hard to do. There's many reasons that make it, if you're guessing at a lot of things. You're guessing at the coefficient of friction, you're guessing at the torque on the bolt, how much is that actually stretching the bolt. And I went down and I got the best way to load a bolt is to, if you've got access to both ends of the bolt, measure the actual strain. You know, put 40 foot-pounds, measure the strain on the bolt, work backwards from that to get the stress on the bolt, and work backwards from that to get the load. Stress equals load divided by area. So, you know, it's really tough because what's 40 foot-pounds? That depends on the friction of the nut from the threads, all that stuff. Then what's the shear strength of a bolt? That's just, you're assuming the bolt manufacturers will say, well, use 60% of the design stress on the bolt as the allowable shear stress. So in this case, 60% of this grade 8 was 90,000 psi, so that's 54,000 psi, and you multiply that times the area of the bolt. It don't give you the allowable shear, because that assumes that the shear across the whole surface, or the whole cross section of the bolt is constant. But it's not. It hits the, you know, when you're shearing something, it hits the edge of the bolt and then it moves across. So it's not a good way. And then there's another thing that I doubt anybody thought of, but I certainly haven't. If you've got a blade in here and straps on the top and the bottom that are squeezing it together. The area of, you know, what percentage of the load is carried by this bolt compared to the percentage of the load carried by this bolt?
Mm-hmm.
Consider a piece of Scotch tape with a rubber band stuck to it, and you pull it on the rubber band. How does that come apart? The end of the rubber band sees no load. It just starts to unzip right at the edge of the tape. Does it not? You know, that's where the stress happens. So it's the resistance of the material from this zone to this zone. You want the strain, all you can say is the strain here is the same as the strain in the blade from here to here. So, but how much is the stress different? Well, the stress on the bolt would be the same here as here, or the retention power. If the retention power of the straps is equal to the retention of the blade section right over there. And that's equal to the area of the straps times the tensile modulus of the straps. In this case, they're both aluminum. The area of the straps is 2 square inches. This one's a 1 square inch, 2 by half. This one's a 1 square inch, 2 by half. Don't worry about the holes because we're just concerned with the unhold part.
Unholy.
The area of the blade is 1.27 inches, which is what, 66% of, huh? Am I losing you?
Yeah.
Too much detail? White did it. Okay, anyway, what it boils down to is this bolt carries about 2/3 of the load, this one carries 1/3, if all other things were equal. All right, I'm done with the bolt thing except for... I just,
You gotta go to the 700
okay.
You gotta go to the 582.
Okay, I just want you to understand that I really leaned on this,
Oh, yeah.
you know what I'm saying? I didn't take it lightly.
I believe that.
You didn't talk about the RPM.
Okay, the RPM to get that 10,500 pounds of tension is, it was 582, which is what we were talking about at the time when I did that. If they go up to 600, then I'll redo them and find out just exactly what the factor of the safety is. At the loads occur at 582. In bending, you know, the bending where it's the worst, either 2 Gs or 0 Gs, had a factor of safety is if you made that factor of safety go away or go to 1.5, which is the minimum what the FAA wants, you'd have the RPM would be 717. So don't go over 717 RPM without checking everything out. Sevens,
That gave us a safety factor of 2.3.
yeah,
You got
and yeah, that still had a safety factor of 2.3. Okay, I'll tell you where that came from is when I was testing these bolts on this fixture, I had a dial indicator on the end of the strap. Show that one? Is it up there? Yeah. So that's measuring where this part of the blade is with respect to the strap. Okay?
Yeah.
You stretch, you put a load on the tip of the blade, and this part will stretch, and then it'll come, and you release the load, and it'll come back. It goes back to 0. I did that in 2,000-pound increments from 0. I did it from 0 up to 16,000 pounds, and it would come back. Over 16,000 pounds of tension, every 2,000 pounds, it would not come back by about 1,000. So 18,000,